so then if this is the graph of the function up here, perhaps something like this, right? We want to be able to compute the volume underneath the graph of the function of this rectangle. And to do this, what we're going to do, and we're going to take one approach here, which is to partition the interval AB and also partition the interval CD. And then with this partition, we get a partition of the rectangle like this into smaller rectangles. In each one of these rectangles here, we're going to want to choose a point. One way to do that is to choose a point UI over here between xi minus 1 and xi. So choose a point UI in there, and choose a point VJ up here between yj minus 1 and yj. So yj minus 1 and yj. Choose a point vj there. Then we'll take a look at the function value at ui vj and multiply that by delta xi and by delta yj. And what this will give you is the volume of this small rectangular parallel pipette here, which lies above the rectangle and has for its top the value of the function. All right, what we want to do with this then is we want to add this up, I going from 1 through n, let's say, and add it up to j going from 1 through m, and then take the limit as the norms of these partitions go to 0. Right. And this is going to define the double integral of f of x and y with respect to area over the rectangle R. This is a rectangle R here. Now, we're going to want this to be the definition of the integral, whether or not the function is positive or non-negative. And several of the properties of integrals are going to follow through with respect to this. That's to say, the integral of the sum of two functions is going to be the sum of those two integrals. The integral of a constant times a function is going to be constant times the integral of a function. And the integral over two regions, R1 and R2, which are adjacent, will add up to the integral over the resulting union of those two intervals. All right. If the region that we're integrating over is more complicated, let's say it's some sort of a region like this, then what we wish to do is as follows. We wish to pick the extreme points A and B and C and D here, the extreme points of this region, and we wish to partition up the intervals AB and CD, and this will result in then a partition, some of whose squares are inside the region. This is the region B here. What we wish then to do is to take the point UIVJ and compute the volume of these rectangular parallel pipettes. Oh, the surface here might actually look something like this. We again form the sum. J goes from 1 through m. Sum I goes from 1 through n. F of ui vj delta xi delta yj, where this sum is over all rectangles which lie inside the region B. And we take the limit here as the norms of the partitions go to 0. You can think of this as one large partition here consisting of all of these rectangles. As the norm of the partitions go to 0, we take this limit, and then this defines the double integral of f of x and y with respect to area over the region B. And again, the integral of the sum of two functions is going to be the sum of the integrals. Constant times a function, integral is going to be but constant times the integral. And if you write this as two regions, the integral over the union of the two regions will be the sum of the two integrals. All right. This defines then the integral over a rectangle or over a general region here. But of course, we're not going to want to use this definition to evaluate the integral unless it's absolutely necessary. Sometimes it is. What we're going to want is some method involving anti-differentiation to find the value of these integrals. And we'll take a look at that next. The method for evaluating double integrals is called the method of iterated integrals, and it consists of doing the following. Over a rectangle, first of all, if the rectangle goes between A and B in the x direction and C and D in the y direction, we do the same thing as before here. Right? We partition this up between A and B, and between C and D. And now what we do is the following. With each line here, for example, in this direction, we take a look at the surface. Our integral is defined to be the double sum f of ui and vj delta xi delta yj, where this is over I, and then j, and then the limit, as the norm of the partition goes to 0. Well, if we fix a particular y value, and look at this sum right here, if we let the limit, as the norm of the partition here goes to 0 in this direction here, what we get is the integral. So that this is going to be the same thing that you have if you took the limit as the partition goes to 0 in the y direction of the sum over j integral from A to B f of x and vi dx delta yj. That's to say we replace this right here with its value in the limit. And now you can think of this as follows. What we're doing then, instead of taking the original sum, taking a small lamina here, we're taking the area of the lamina times delta y, and we're summing this up over j, and we're letting the partition, if this partition here is q, let's say, we're looking at the limit as the norm of q goes to 0. And this then corresponds to an integral of this function here with respect to y. That's to say, this is the integral from A to B of f of x and y dx. Right? You integrate this with respect to x for fixed y, and then you integrate that with respect to y from C to D. Right? And so that the volume underneath f, if f is non-negative, is going to be given by this iterated integral. And here the parentheses are not always written, but they're always understood. And this is with respect to x fixing y. And then you integrate the whole, or this is with respect to x fixing y, and you integrate the whole thing with respect to y. Let's take a look at an example. A simple one. Let's suppose we have f of x and y equals 2 of x plus 2/3 y. This looks like this. And this is a graph. The graph of this is a plane. And the xz plane here, when y is equal to 0, looks like x. Over here, it looks looks like 2/3 y. So the plane comes up here like so. And let's look at this for values x between 1 and 2, and for values y between 1 and 3. So I'm over this rectangle here like this. We want the volume underneath this plane and above the rectangle. Well, what we should do with this then is the following. We should integrate x plus 2/3 y with respect to x first from 1 to 2, and then integrate that from 1 to 3 with respect to y. Now, the same argument that was given here, it indicates that for a rectangle, you can do this the other way around also. We could integrate from c to d with respect to y first, and then integrate from a to b with respect to x. We would get the same result. We would just be doing things in this direction first, and then the other. All right, at any rate, we wanted to integrate this with respect to x. So fixing y and antiderivative of this with respect to x is going to be x squared over 2 plus 2/3 xy. Right? Y is fixed here, so an antiderivative of this is going to be 2/3 x times y. We want to evaluate that from 1 to 2, and then integrate from 1 to 3 with respect to y. And by evaluating this from 1 to 2, we mean evaluate it from x equals 1 to x equals 2. All right? This is going to give us then, at x equals 2, we're going to have 4/2 plus 2/3 times 2y. Right? That's the value at x equals 2, minus the value at x equals 1, 1/2 plus 2/3 y. And now we want to integrate that with respect to y from 1 to 2. Right? And I'm going to stop here because this is just your ordinary integral. You integrate this function here with respect to y from 1 to 2. You find an antiderivative with respect to y. Take the value at 2 and subtract the value at 1. Throughout this, we'll stop when we reduce the things to a previous type of problem. These problems with multiple integrals tend to get to be very large, but at a certain point, they're just work that is similar to work that's been done before. So here's how to compute the integral of the function f over a rectangle, and here's an example that's fairly simple. I want to take a look now at how to compute volumes and other things that involve multiple integrals here, double integrals. When the region that you're integrating over is not a rectangle. Right? Well, there are two types of simple regions. One of them consists as follows. You've got a function f of x and y up here, and the region may be between A and B, like so, but then the other boundaries of the region, maybe it's two functions of x. Let's say h of x here and g of x over here. Right? What you can do with this then is you can partition it in this direction here and integrate in this direction first, giving you some sort of cross-sectional area here, which you will then integrate from A to B. So that, for example, if we've got f of x and y here, and we want to find the double integral over this region, call it B, of f of x and y with respect to area, this is going to be equals to the integral from y equals g of x to y equals h of x of f of x and y. Here we're going to integrate respect to x, with respect to y, we're integrating in this direction here, the y direction. So we'll integrate our function here with respect to y, fixing x. Then we want to integrate the result that we get from a to b with respect to x. And this double integral then will give us the volume underneath the graph of this function. Right? The second possibility is that you have got a region which is simple in the other direction. Say something like this. Right? Where this goes between c and d, and this perhaps is g of y, and the larger function is h of y, so x equals h of y is this, x equals g of y is that one. Right? In that case, the integral over this region here, d, right, can be computed as the integral from g of y to h of y, that's to say from x equals g of y to x equals h of y, f of x and y. Here we want to fix a value here and integrate across this way here. So this is going to be with respect to x. We wish to integrate from c to d with respect to y. And this will give you then the volume underneath the function f. You want the volume of between two functions f1 and f2. If this one is f2 here, we want the volume over that region. Then you can take the integral of f1 minus f2 over the region, and that will give you the volume between f1 and f2 if f1 is the larger one and f2 is the smaller. If the region isn't simple, frequently you can break it up into regions which are. For example, here's a region which is not particularly simple, and what you can do with this, though, is to break it up into several regions here, right, which presumably are simple. In particular, let's say if this was in the xy plane, then this region right here would be simple in this direction, this one would be simple in this direction, and this one would be simple in this direction. So you get the integral of a function f defined on this region by integrating over this part here first, and then adding the integral over this part, and adding the integral over that part. Right? So for simple regions, and for regions that can be broken up into simple regions, you can find the integral by this method right here. Let's take a look at a specific example of an iterated integral over simple region. Let's suppose that we have f of x and y equals to x squared plus 2y squared. This is a paraboloid. Looks something like this. Y equals x. When y is equal to 0, z is x squared, so you have a parabola opening like so. When x is equal to 0, you have z is equal to 2y squared, so that's a parabola that looks something like this. The result is a paraboloid. I guess like this part right here is supposed to be y equals x squared, so this looks like this. This comes here, and this here. Okay. Let's look at this in a region where bounded by y equals x and y equals x squared. So for that y equal x here like this, and y equal x squared like so, so this is y equals x squared, and this is y equals x, then we want to look at the region something like this. It's going to be a surface that's going to be a region here that looks something like this. That's to say, now, the double integral of f of x and y with respect to area over this region, if this region is called B, is going to be equals to, we can integrate from one side of this to the other here. That's to say, integrate from y equals x squared, the smaller function, to y equals x, our function x squared plus 2y squared. And we're going to want to integrate with respect to y then. And we would integrate from 0 to 1 this with respect to x. That's parentheses are understood to be here and here. Right? So we first integrate this with respect to y, and then that's going to give us a function of x, which we integrate from 0 to 1. Right. And the antiderivative of this is with respect to y is going to be x squared y plus 2y cubed over 3. We want to evaluate that from x squared to x, and then integrate from 0 to 1 with respect to x. That's to say, we evaluate it from y equals x squared to y equals x. So if we put x in here, we get x cubed, putting x in for y, plus 2/3 x cubed, minus the value of y equals x squared, that's x to the 4th, and then minus here 2/3 y to x to the 6th. X cubed goes in here for, x squared goes in here at y cubed, and we end up with x to the 6th. We want then to integrate this from 0 to 1 with respect to x. Well, what have we got here? We've got 5/3 x cubed, so that this is going to be equal to 5/3 x to the 4th over 4, minus x to the 5th over 5, minus 2/3 x to the 7th over 7. We evaluate this then from 0 to 1. And that's going to give us 5/12, 5 over 3 times 4, minus the 5th, minus 2/21. So this right here then should be the volume above this region and underneath the surface. We could have done this elsewise. We could have come from this direction here and this direction here, and notice that here x equals y, and here in this direction here x equals the square root of y. Right? So what we could have done with this is we could have integrated from the lower function y to the upper function the square root of y, our original f, x squared plus 2y squared. Here we integrate first with respect to x, and then integrate from 0 to 1, because we would be going here from 0 over to 1 in this direction with respect to y. The original 0, 1 in this integral was the 0, 1 in this direction right here. This 0, 1 is from here to here. All right? And now, here now we integrate with respect to x first, so we get x cubed over 3 plus 2xy squared. We evaluate that then from x equals y to x equals the square root of y, and then integrate from 0 to 1 with respect to x. So what we do then with this is we put the square root of y in here for x, and in both places here, we subtract what we get if we put y in for x, and then we integrate with respect to y. The second integral is with respect to y. So we're going to end up with a function of y in which we integrate with respect to y, That's just the ordinary Riemann integral, and it should give us the same answer that we got right here. So here then is an example of how to find an iterated integral. We want to take a look at some applications of the integral, some places where the integral occurs, and mass and moments are instances of this. These concepts actually occur both in physics and in statistics, and if you've got a region B, let's say, in the plane, right? And this goes between two values here in the x direction and two values in the y direction, in which case you partition this interval and this interval, resulting in small rectangles contained in B. Then one possibility is that this is a lamina, B represents a lamina here with a variable density given by rho of x and y in if we're thinking of this in terms of density in physics, we're talking about in, let's say, mass per unit area. Right? Could also be in weight per unit area, or this could even be a charge density in unit of charge per unit area. And then what we would want to do is we would want to take and add up rho of ui vj. That's the amount of mass per unit area, delta xi, delta yj, and this would give approximately the total mass, and we would then want to take the limit as the norm of the partition goes to 0, and this is going to correspond to the double integral over b of rho of x and y dy dx, or with respect to area. If we wish to compute the moment of this region about, say, the y-axis, this is abbreviated the moment about x equals 0, or the moment about the y-axis, we could get this by integrating over b. Now what we would do is we would take this small piece here and we would multiply its mass by the distance to the y-axis, that's to say x, rho of x and y with respect to area. This would give the moment about the x-axis. The moment about the y-axis. The moment about the x-axis, or y equals 0, or the moment about the x-axis is given by the double integral over b of y rho of x and y with respect to area. And now, just as before in the calculus 1 applications of moments, we can get the point with x bar, y bar, which is called the center of gravity. This is the point where this will balance. X bar is given by the moment about the y-axis, let's just say about x equals 0, divided by the total mass. Y bar is given by the moment about the x-axis, divided by the total mass. In the event that rho is a constant, if rho of x and y, let's say, is equal to some constant value rho, then when you perform this division here, the rho's cancel, because you've got rho in one integral and rho in the other integral, and they come out of the integral. X bar is equal to the integral, the double integral of x with respect to area divided by the double integral of 1 with respect to area. The rho cancels, it can come outside of the integral here, and y bar is equal to the double integral of y with respect to area divided by the double integral of 1 with respect to area. And there's no rho involved, and in this case, x bar, y bar is called the centroid. It's a geometrical property of the shape. Right? If rho is equal to 1, right, the double integral of 1 with respect to area over b is going to be equal to the area of b. Right? So that if rho is equal to 1, then the mass per unit area is 1, and the mass equals the area, and so we can compute the area of the region B here by integrating 1 with respect to x, not with respect to y, over the region B. So here are some examples of integrals that come from the concepts of mass and moment. Let's take a look now at a simple example involving mass and moments here. Well, let's suppose that we're looking at the region in the plane between y equals x squared and say y equals 4 in the first quadrant. So this region right over here, x here goes between 0 and 2. Y goes between 0 and 4. And let's suppose that rho of x and y is equal to 1, so that what we're looking at is the area when we compute the mass. That's to say, the area here of this is going to be equal to the double integral of 1 with respect to x and then with respect to y over this region B here. Right? This is going to be the exact thing that you get if you integrate it using calculus 1 methods. To find the area of this, you would integrate from 0 to 2, for example, 4 minus x squared dx. Right? Here, you're going to want to integrate, thinking of this as a simple region, from one end to the other, that's to say from x squared to 4, our function 1, with respect to y. Then we want to integrate from 0 to 2 with respect to x. Right? And this is going to give us then what? The integral from 0 to 2, we've got 1, and antiderivative is x, evaluating at the endpoints. We have 4 minus x squared. Right? And now we want to integrate this with respect to x. So we've got the same integral that you get from calculus 1 here. And now this is going to be equals to 4x minus x cubed over 3, evaluated from 0 to 2, which is going to be 8 minus 8/3, or 16/3. This will be the mass of this or its area. Now, if we want the moment about the y-axis, x equals 0, right? We then want to do the double integral of x with respect to area over this region B. That's to say we want to integrate from 0 to 2, and then integrate from x squared to 4, x dy dx. So this is from y equals x squared to y equals 4. This is going to give us the antiderivative for x with respect to y is xy. We want to evaluate that from y equals x squared to y equals 4, and then integrate from 0 to 2 with respect to x. So this will be the value at 4 let's say when y is equal to 4, we're going to have 4x. The value at x squared, when y is equal to x squared, is going to be x cubed. So 4x minus x cubed. We want to integrate this from 0 to 2 with respect to x. And the antiderivative now is going to be 4x squared over 2 minus x to the 4th over 4. We want to evaluate that from 0 to 2. That's to say we're going to get 4 times 4 is 16 over 2 is 8. Minus 16 over 4 is 4. So that this integral is 4. Right? And from this then we can compute x bar. It's the moment about x equals 0. 4 divided by the total mass, in this case the area, 16/3, so times 3 over 16. So this gives us then x bar. To compute the moment about y equals 0, we wanted to take the double integral of y with respect to area. This is going to be the integral from 0 to 2, integral from x squared to 4 of x of y dy dx, and then the derivative of y with respect to y is y squared. So we're going to get y squared, evaluate from x squared to 4, and then integrate this from 0 to 2 with respect to x. Right? So we want to go from y equals x squared to y equals 4. At 4 we're going to have 16. At x squared we're going to have x to the 4th. So 16 minus x to the 4th. We want to integrate that from 0 to 2 with respect to x. Right? And antiderivative is going to be 16x minus x to the 5th over 5. And evaluating this from 0 to 2 is going to give us 32 minus 32 over 5. Right? Or 4/5 of 32. Right? This is the moment about y equals 0. If we want y bar now, we take the moment about y equals 0, 4 times 32 over 5. We divide by the total mass, 16 over 3. So this is times 3 over 16. And this then is going to give us y bar here. So here is an example using double integrals of how to compute moments both about the x-axis and the y-axis and the centroid. We wanted to say something now about integrals involved with computing moments of inertia. The moment of inertia comes from something like this. First of all, let's imagine that we've got some sort of a region B here, and we've partitioned it up, and this is one of the rectangles. We wish to rotate this region B about the origin. We can consider this small piece here to be to act like as if it were essentially a particle, and then kinetic energy of this is going to be 1/2 the mass times the velocity squared. Right? Now, if we're rotating this about the origin, the velocity of this, if it's got a constant angular motion here, is going to be r times omega, where omega is angular velocity. So that we get that the kinetic energy is given by 1/2 r squared Now this is going to add up, and if we wish to add up all of these distances here, the radius, if you want, is to say ui squared plus bj squared. We wish to add up all those distances squared, and then the quantity of mass here is given by the density, rho at ui vj, delta xi delta yj times the area, the density times the area. This is times the distance, so this is density times area. That gives the mass. Right? Multiply this by the distance and add these up over I and j. Right? This is going to give you approximately the moment of inertia. We took the limit here as the north of the partition goes to 0. This is going to give the moment of inertia. And so the moment of inertia here for a lamina with shape B and density rho of x and y is given by the double integral over B x squared plus y squared rho of x and y with respect to area, which would normally be done as an integral with respect to x and with respect to y. We wish to rotate this about the x-axis. We then have a quantity which we call I sub x, the moment of inertia about the x-axis. And here we wish to take the distance to the x-axis, that's to say y, and square it, multiply by rho, and integrate this with respect to area over the region B. Right? The moment about the y-axis, the moment of inertia. You can also write this as the moment about y equals 0, moment of inertia about y equals 0, and this is the moment about x equals 0. This is going to be the double integral over b. We now want the y-axis here, so we take the distance of the y-axis, which is x, and square it, rho of x and y, integrate with respect to area over the region B. And so moments of inertia then involve integrals, and if you know rho, the integrals are simple, straightforward to calculate over the region B, which describes the particular shape of the lamina. We want to now look at the surface area of the graph of the function f of x and y, and develop the formula for which will give us that area. It involves an integral. This might be over a region B, right? And we've got some sort of f of x and y over this region. Right? We would want to partition up this region here, resulting in small rectangles contained in B. And what we wish to do is to look up here at the surface and see what's happening. Right? If we look at this, if this function is differentiable, and in fact we're going to assume it's continuously differentiable, at this point here, let's say uv, right? We're going to have a tangent plane. We're going to have two vectors here like so. Well, let's say this is the point x, y. And let's make these two vectors u going in the x direction and v going in the y direction. Now, if we go in the x direction 1 unit, the vector u is going to be slanted, and it's going to go in the k direction here, exactly. So 1 unit in the x direction is going to go in the k direction, partial of f with respect to x, so that the vector u we can write as, we go delta x in the x direction, it's going to be delta xi, and then plus the partial of f with respect to x at this point times delta x k. So that's going to be the vector u here. The vector v lying in the tangent plane and going from here to here is going to be delta y in the j direction, the y direction here, and then it's going to go upward or downward depending on whether this is positive or negative, partial f with respect to y at x and y times delta y. Now, this is going to produce a small rectangle here which lies approximately on the surface. And the area of that rectangle is going to be the cross product of u and v. If we take u and cross it with v, take the magnitude of that cross product, that's going to be the area of that small parallelogram. It's a parallelogram up there, because this cross product is also going to be a normal vector to the surface of f of x and y. Right? So we want to remember what this vector is. Well, what is it? Let's take the cross product. We've got I cross k, and in each case here we're going to have delta x times delta y, so let's factor the delta x, delta y out. And so what we've got then is 1, I cross k is minus j, so we end up with minus partial f with respect to y times j. I'm going to delete the x and y here. And then we've got ij is k, delta x, delta y, so that this is going to be plus k. Then we've got kj. K crossed with j is minus I, so we get minus the partial f with respect to xi. And now k crossed with k is 0. So this cross product is this. And this quantity right here, partial with respect to x, negative of it, minus partial with respect to y, 1, is a normal vector. And the magnitude of this, take the magnitude of this vector, it's going to be the area of the parallelogram. So what we're going to want to do with this is we're going to want to sum this up over the partition, right? And that's going to correspond then to an integral. Well, over b, delta x, delta y here is going to correspond to dx, dy. And now we want the magnitude of this vector, that's to say it's the square root of partial f with respect to x squared plus the partial f with respect to y squared plus 1. So that the surface area is given by this formula here. Right? Now, under most circumstances, this is not an easy integral to evaluate, because when you take a function f, take its partial with respect to y squared, take the partial with respect to x squared, add 1, take the square root, you don't end up with anything that's particularly easy. However, in some instances you do. In particular, let's say if we have f of x and y describing a plane, let's say 3x plus 4y plus 5. And let's suppose we wish to know the area above the region when x is between 7 and 8, and when y is between 1 and 2. Well, we're going to want then the integral from 7 to 8, and then the integral from 1 to 2 here, with respect to x going from 7 to 8, and then with respect to y, and now we want to take the square root. The partial of f with respect to x is 3, so this is going to be 9. Partial of f with respect to y is 4, so this is going to be 16 plus 1. So we take the integral of this over here, and this is going to be what, 9, 16, 25, 26. We're integrating over a square of size, a constant over a square of size 1, so square root of 26 is going to give you the surface area of this linear, well, this function whose graph is a plane over this region. However, in general, this area here frequently needs to be approximated, but this is the integral that gives it. note also the similarity between this and the formula for arc length. Right? That makes this a very memorable formula. I'm going to take a look now at triple integrals. Actually, multiple integrals are handled in the same fashion. There are applications for such things. If we take in three-dimensional space some sort of a region B, right, say bounded in the x direction between A and B, in the y direction between C and D, and in the z direction between E and F, right? We can then integrate, let's say, a function g of x and y, g, x, y, and z. Find on this region, G is going to associate with each point in the region a value, right? A real value, and we're going to want to look at the triple integral of G of x, y, and z with respect to volume over the region B. And this is gotten by means of partitioning up A, B, C, D, and E, F, looking at little cubes in here. Right? Taking the value of the function at a point in the cube times the volume of the cube, adding this up and taking the limit. But what you do in general here is you evaluate this as a triple integral where you integrate G of x, y, and z. First of all, let's say in one direction, x direction, and then in the second direction, the y direction, and then the third direction, the z direction. We'll take a look at how to do some of that next, but first of all, let me indicate some of the applications that you can have to these triple integrals. If g of x, y, and z is a density, say it's rho of x, y, and z in mass per unit volume, right? Then the triple integral over B of G of x, y, and z with respect to volume is equal to the total mass. If this were in charge per unit volume, then this would give you the total charge. If it were in weight per unit volume, the total weight. Right? If you wish to compute the centroid of this region B here, or the center of gravity of the region B, what you wish to do is first of all compute the moment about, let's say, the xz plane here, the moment about the xy plane, and the moment about the yz plane. The moment about the xz plane, that's the moment about y equals 0, the xz plane. You now take this small piece and you compute its distance here, which is going to be y. So y times g of x, y, and z, and integrate that over b with respect to volume, and this will give you the moment about y equals 0. The moment about x equals 0 is the triple integral over b of x, g of x, y, and z with respect to volume. The moment about z equals 0 is the triple integral z, g of x, y, and z with respect to volume over b. And now x bar is equals to the moment about x equals 0 divided by the total mass. Y bar is the moment about y equals 0 divided by the total mass. And z bar is the moment about z equals 0 divided by the total mass. Right? This is moments of z equals 0 here, huh? And the point x bar, y bar, z bar is going to be a point where this thing would balance. That's to say, if you put a hook in here and hung it from a string, it would fall down so that this was in direct line underneath the string, triple integral of the distance of a pointer to the origin, that's squared, that's x squared plus y squared plus z squared, times rho with respect to volume, the integral over b, where rho here is the density. Right? If rho is equal to 1, we then get the volume of this, of b, is given by the triple integral over b of 1 dx dy dz. So if you integrate 1 over b, you will get the volume of b. So here are several analogous applications here of triple integrals to objects in three-dimensional space. We'll take a look at how to evaluate triple integrals. And for this purpose, one frequently divides things up into simple regions. There are essentially 6 different ways to go about this, as will become apparent here. If we've got a region in three-dimensional space here, one way in which it can be simple is that it's between two surfaces here, z equals g of x and y, and z equals h of x and y. Let's put h on the top. So it's between g of x and y and h of x and y. And then when we come down here, it can be between, for example, a and b, and between two functions of x. Let's say y2 of x and y1 of x. So that our region is all these points up here between a and b, between y1 and y2, and between g of x and y and h of x and y. So the region consists of all z, where g of x and y is less than or equal to z is less than or equal to h of x and y. Y is between y1 of x and y2 of x, and x is between a and b. So there's a description of our region. And now by turning this around in various directions here, you get the possibility of 6 simple types of regions, or 6 ways to describe a simple region. The region isn't simple. What you want us to try and do is to break it up into regions which are simple, integrate over each of those regions, and add up the resulting integrals. Let's take a look at an example here. Let's suppose that we've got f of x and y equals to xy plus z. We wish to integrate it over the sphere of radius 2. Right? This is supposed to represent the sphere of radius 2. That's to say x squared plus y squared plus z squared equals 4 is the equation of the sphere. Now, the sphere we can view as 2 functions of x and y. There's an upper function, the square root of 4 minus x squared minus y squared, and there's a lower function, the square root, the negative of the square root of 4 minus x squared minus y squared. Right? So to integrate our function f, xy plus z, over this region here, b, right? With respect to volume, what we wish to do is we want to integrate from z equals minus the square root of 4 minus x squared minus y squared to z is the square root of 4 minus x squared minus y squared, xy plus z. When we've done that, we will then have produced an integral from the bottom to the top at each point x and y, and say from this side to this side. Now this side right over here this is the circle of radius 2, so this side right here is described by the square root of 4 minus x squared. This other side of the circle is the square root of 4 minus x squared, the negative of that. So we next wish to integrate from y equals minus the square root of 4 minus x squared to y equals the square root of 4 minus x squared. And finally we wish to integrate, so this is, we first integrate with respect to z, then we integrate with respect to y, and then we want to integrate with respect to x from minus 2 to 2, because this goes in the x direction here from minus 2 forward to 2. Right? And now to do this, what we do is we find an antiderivative of x, y, z with respect to z. That's going to be x, y, z plus z squared over 2. We want to evaluate that from z is equal to the negative square root of 4 minus x squared minus y squared to z is equal to the square root of 4 minus x squared minus y squared. Okay? And then we wish to integrate that with respect to y and then with respect to x. Okay? When we do this evaluation here, we're going to put this in here for z, we're going to put this in here for z, and we're going to subtract the two, and we'll have no z's left. So we'll be integrating a function of x and y with respect to y, and then with respect to x, and that's the type of thing that we've already done. Right? So here is how to, right, not the answer, but how to evaluate the volume of this if its density is x, y plus z, and it's the sphere of radius 2 centered at the origin. Let's take a look at another triple integral here. Let's suppose we've got f of x, y, and z equals to say x squared plus yz. We want to integrate it over the region in the first octant that lies underneath the plane x plus 2y plus 3z equals 6. So this is going to look like this. What happens here? Well, when y and z are 0, x equals 6. So this comes out 6 units like this. 3, 4, 5, 6. There's a point on the plane. When x and y are equal to 0, z is equal to 2, so it goes up 2 units up here. When x and z are equal to 0, y is equal to 3, so it's over here. This is this plane right so, like so. We now want to integrate our function f of x, y, and z over this tetrahedron shape right here. So for that purpose, let's integrate with respect to z first, fixing x and y, and we then wish to, we can find that z is equals to 6 minus x minus 2y divided by 3. So what we wish to do is to integrate f over this region, let's call it B here, with respect to volume. What we do is we integrate, first of all, our function x squared plus yz from 0, from z equals 0, to 6 minus x minus 2y over 3. With each xy here, then that will give us the value of the integral of f from 0 to that point on the plane. Right? We want to do this with respect to z. And then next we wish to, let's say, fix x and integrate with respect to y. So we're going to want to integrate from this side here to that. Let's just say we're going to want to integrate from 0 to the equation of this line. Well, when z is equals to 0 here, we get this line is x plus 2y 6, or that y is equal to 6 minus x over 2 is the equation of that line. So we now wish to integrate from y equals 0 to y equals 6 minus x over 2. Right. We'll now have integrated with respect to y and with respect to z. Finally, we wish to integrate with respect to x from one end to the other here. That's to say from x equals 0 to x equals 6 with respect to x. And this then is going to give us the integral. All right. To perform this integration, what we want to do here is we want to first anti-differentiate this with respect to z. We're going to get x squared z plus y z squared over 2. And when we evaluate that from 0 to 6 minus x minus 2y over 3, then integrate from y equals 0 to 6 minus x over 2, and integrate from 0 to 6. This is now with respect to y and then with respect to x. Let's just do one more step of this. Let's evaluate this from z equals 0 to z equals 6 minus x minus 2y over 3. Right? When z is 6 minus x minus 2y over 3, we get x squared times 6 minus x minus 2y over 3 plus y over 2 times 6 minus x minus 2y over 3 quantity squared. We now wish to integrate this with respect to y, and then integrate with respect to x. And the thing to note here is that what we've got is a function of x and y. If you don't, you've made some sort of an error at this stage. We now want to integrate this from 0 to 6 minus x over 2 with respect to y. When that's completed, you should have only a function of x. We want to integrate it from 0 to 6 with respect to x. So here's an example of how to do a triple integral. We've reduced it at this stage here to doing that of a double integral. You now want to take a look at how to find the integral of a function which is given in cylindrical coordinates. So that we've got f of r and theta and z here. Now, if we look at a particular radius r here, an angle theta, so if this is an angle theta, and this is the radius r, and a height z, like so, then this is the point right here, r theta z. But what happens now is this. An element of volume at this point looks like this. If we take the projection of the element of volume down here, it's going to look like so, and that element of volume is going to look like this up here. It's not going to quite be a rectangular parallel pipe, but it's going to be rounded on the outside here. But in the limit, it's essentially going to be a parallel pipe. So that delta V here is going to be equal to, this side right here is delta R. So delta R is this right here. This side right here is R delta theta. So that the other side, the second side of this is R delta theta. And this side right here is delta Z. So that the approximate volume of this is going to be equal to R delta theta, delta Z. And so if we've got our function as a function of R, theta, and Z, in order to find the integral of it with respect to volume over a region here, B, let's say, what we want to do is we want to take f of R, theta, and Z, and then integrate times R dr d theta dz. This R will always be in here. It's a multiplier that gives you the correct volume of the equivalent of a partition element in rectangular coordinates. So that, for example, let's suppose that we wish to integrate over the region underneath z equals r squared. That's going to look like a paraboloid here in the first octet, and between let's say r equals 0 and r equals 2. So, and let's suppose that our function f of r, theta, and z is equal to, let's say, theta r squared. Right? We then wish to integrate this, and this is a simple region in cylindrical coordinates. That's to say, z goes between 0 and r squared. So we integrate this theta, our function theta r squared. We now have to multiply by r to get the correct integral. And then we integrate this with respect to z. We now have, let's say r going between 0 and 2. So we integrate this with respect to r between 0 and 2. And then theta goes between 0 and pi over 2. So we integrate this with respect to theta between 0 and pi over 2. Now, this quantity right in here is now an ordinary integral. That's a function of r, theta, and z. And it's an ordinary integral. If we integrate this with respect to z, for example, we're going to get theta r cubed z. We want to evaluate that from 0 to r squared, and then integrate from 0 to 2 with respect to r, and from 0 to pi over 2 with respect to theta. We evaluate that from 0 to r squared. That's to say this is from z equals 0 to z equals r squared. We get theta r to the fifth. So this then becomes the integral of theta r to the fifth with respect to r and with respect to theta from 0 to 2 and from 0 to pi over 2. Now this is an ordinary integral here. We're going to get theta r to the sixth over 6. And when we evaluate from r equals 0 to 2, we're going to have theta times 2 to the sixth over 6. We're going to want to integrate that from 0 to pi over 2 with respect to theta. When we integrate this with respect to theta, we get theta squared over 2. So that for an integral here, we get 2 to the sixth over 6. We have theta squared over 2. We evaluate it from 0 to pi over 2, and that's going to be pi over 2 squared over 2. So times a half. So all together here, then 2 to the sixth over 6 times pi squared over 8 is going to be the value of this integral in cylindrical coordinates. You need to remember that this quantity r is always present here when integrating a function over a region in cylindrical coordinates. You integrate r d theta dz. Now let's take a look at the integral in spherical coordinates, and it's a little trickier than it is in cylindrical coordinates. Suppose that we've got some function of rho, theta, and phi, right? Having a value at each point here in space, where this is the angle phi here, it's this angle down in this direction. The angle theta is over here, and rho is this length right here. Now, what we end up with in spherical coordinates, right, is we've got a small element in the rho direction, an element in the phi direction, and an element in the theta direction. So you end up with something that looks like this for an element of volume. If we were to project this side right here downward, it's going to look like this. recall that this side right here has r delta theta for its length. And so up here, what are the sides going to look like? Well, this side right here is going to have delta rho. So an element of volume here, delta V, is going to involve delta rho on one side. This side right here, right, is going to be rho delta V. And we need to multiply this radius here times the change in, that's this side right here is going to be rho delta phi. We need to multiply the radius here times delta phi here to find out this length. The third side right here, or if you like back here, if we project it down here, we get r delta theta. Now r is equal to rho sine phi. So this is equal to rho sine phi delta theta. It's this third side. Rho sine phi delta theta. So that all together here, then, for an element of volume, we're going to get rho delta phi times delta rho times rho sine phi delta theta. So rho squared sine phi delta theta. So that when you do the integral here, this is the multiplier here of the value of the function. You want to take the value of the function at a point in here and multiply by the volume, and so that the integral is going to look like a triple integral over whatever region it happens to be B of f of rho theta and phi. But now you're going to have rho squared sine phi, and then these in whichever order is convenient here for doing the integration. For example, d rho, d theta, d phi. And this is a multiplier in either case. Let's see how this might be done. Let's suppose that we wish to, say, let rho go between 0 and 2, and theta go from theta between 0 and pi over 6, and rho is going to go from 0 to 2, and let's suppose we let phi go between, here's phi, it's going to go from 45 degrees all the way down to 90 degrees. So we're going to have phi between pi over 4 and pi over 2. Right? This is going to produce a region that looks something like this. Right? And let's suppose we want to know the volume of that region, in which case we ought to integrate 1. We need to multiply by rho squared sine phi. Now here, this is a rectangle, so to speak, in spherical coordinates. So if we integrate d rho from 0 to 2, and then we integrate with respect to theta from 0 to pi over 6, and we integrate with respect to phi from pi over 4 to pi over 2, this ought to give us the volume. Right? So integrating with respect to rho first here, we're going to get rho cubed over 3 sine phi. We want to divide by rho cubed over 3 from 0 to 2, so we're going to get 2 cubed over 3 minus 0 cubed over 3. And now we want to integrate this with respect to theta, and then with respect to phi, from 0 to pi over 6, and from pi over 4 to pi over 6, to pi over 2. Right? The integrator of this with respect to theta, this phi is fixed in here, so it's just sine phi times theta. When we evaluate that from 0 to pi over 6, we're going to get our 2 to the cubed over 3, or 8/3, times pi over 6, times sine phi. We want to integrate that from pi over 4 to pi over 2 with respect to phi. Antiderivative of sine is minus the cosine, and so what we're going to get here is 8/3 times pi over 6 times cosine of phi, evaluated from pi over 4 to pi over 2. Right? Cosine of pi over 2 is 0. Cosine of pi over 4 is square root of 2 over 2. This should be minus the cosine of phi, so that we're going to get for our answer here 8/3 pi over 6 times the square root of 2 over 2. So this then is the volume of this region here. The antiderivative of sine should be minus cosine, and we want to evaluate it between here and here. Okay, so here's an example then of what's essentially a very simple region in spherical coordinates, and how to integrate to find its volume. We need to integrate 1 times the multiplier here for spherical coordinates. It's essential to memorize that rho squared sine phi is that multiplier. Let's take a look at a more complicated region here. Let's let f of rho theta and phi be equals to rho theta, for example, here. And let's suppose we want to look at the region as we get like this. If we consider the points that are outside the sphere of radius 1, all right, in the first octant here, so they're going to look something like this. And now let's take a circle here of radius 1 here, and let's consider the points in here to be rotated in this direction here, producing something that looks perhaps like this. All right. These points right here are part of the region, and it looks something like this. So basically what we've done here is we've taken a circle, radius 1, taken another circle of radius 1, and we've rotated this about the z-axis. Right. Now, if we look at this right here, we can write the equation for this by noting that rho equals 2 sine phi would have a circle here, like so, for its graph. Recall polar coordinates, right? So what we wish things to do is we wish to integrate rho theta. We have to multiply by rho squared sine phi, the multiplier. We now wish to integrate this in the rho direction from 1 to 2 sine phi. So from rho equals 1 with respect to rho to 2 sine phi. We then wish to integrate that for the first octant here. We wish to integrate that with respect to theta from 0 to 2 pi over 2. And then we wish to integrate with respect to phi from this angle right here down to 90 degrees. Well, this angle right here, if these these are two circles, is going to be, this angle inside here is going to be 60 degrees, so this will be 30 degrees. So we wish then to integrate from 30 degrees, or pi over 6, to 90 degrees, or pi over 2, with respect to phi. Right? Now we take this whole quantity right here. Now this is an ordinary integral. That's to say we integrate with respect to rho first here. We're going to have theta times sine phi. We've got rho cubed here, so we should have rho to the 4th over 4. We want to evaluate this from 1 to 2 sine phi, and then integrate with respect to theta and with respect to phi. From 0 to pi over 2, and from pi over 6 to pi over 2. Right? So here we take this and evaluate it from rho equals 1 to rho equals 2 sine phi. We're going to have theta sine phi. Now we've got 2 to the 4th, or 16 over 4, so this is going to be 4 sine to the 4th of phi, right, minus, at 1, 1 to the 4th over 4, so minus a quarter. Right? And we want to integrate this from 0 to pi over 2 with respect to theta, and then integrate that from pi over 6 to pi over 2 with respect to phi. Notice that what we've got here is a function of phi and theta. It's got a sine to the 5th power of phi in it, right? But that certainly is doable using methods from calculus, and it's got a sine in it. So I'm going to stop at this point right here. There's still some work to do here, but what this is now is it's a double integral where the variables are theta and phi, and you integrate between these limits. This is theta, from theta equals 0 to theta is pi over 2. This is from phi is pi over 6 to phi is pi over 2. I take a look now at a general method for finding a formula for surfaces and for the surface area. It goes like this. Here we've got our space x, y, z, and what we imagine here is that we've got a plane, a UV plane, and a region in here, perhaps a rectangle. Right? U going from A to B and V going from C to D. Now what we have here is a function which maps this into our space, resulting in some sort of a surface. Right? That's the stage point here, goes to some point in three-dimensional space. If we partition up AB, we end up with something that looks like this. Right? And if we partition CD, we end up with something in this direction right here. And one of these stripes here, for example, may go through here like so. And a stripe in the other direction through here like this. We're going to consider this to be the vector value function, r of u and v. It's going to take a point uv here, and it's going to correspond it to a point x, y, z. So r of uv will be equals to x of u and v, y of u and v, z of u and v. Now, what we want to do is we want to consider these two vectors here, right? Corresponding to the partition here. That's to say, what we want to do is we want to look at r of u plus delta u minus r and v minus r of u and v. That's going to be this vector here, for example. consider the other vector, which is going to be r of u and v plus delta v minus r of u and v. Right? What we'd like to do is we'd like to take the cross product, take the magnitude of it, and say that's approximately the area, but we're not going to quite do that. All right? That's to say, if you consider this in terms of x, y, and z, all right, this is approximately equals to partial of x with respect to u. This one right here is approximately equal to partial x with respect to u, this vector, delta u, partial of y with respect to u, delta u, partial of z with respect to u, delta u. And this vector right here is approximately equals to partial of x with respect to v, delta v, partial of y with respect to v, delta v, partial of z with respect to v, delta v. We're going to denote this first one here as r, partial of r with respect to u, delta u. The second one we're going to denote by partial of r with respect to v, delta v. What we want to do with these is we want to take their cross products. Right? That's going to give us a normal vector in its magnitude. The magnitude of this cross product is going to be the area of the parallelogram that approximates the area of this surface. Right? Well, what is this? This is r with respect to u crossed r with respect to v, delta u, delta v. We take the magnitude, we can factor the delta u, delta v out. If we add this up, all right, and take the limit as the norm of the partition goes to 0, this ought to give us the surface area. And so the surface area is given by the following formula. It's going to be the double integral. In this case here, we go from a to b and then from c to d of the magnitude of r, partial of r with respect to u, cross partial of r with respect to v, d u dv. So here's a formula then for the surface area. Right? When the surface is given by a vector valued function r of u and v, where u and v come from a plane. We want to take the formula from the last episode and use it to derive surface area for cylindrical coordinates. The reason for this perhaps is just to show how to do such a thing, and the fact that the formula simplifies to something that's fairly nice makes it somewhat of a usable formula. We suppose that what we've got here is a function z of r and theta, right? Defined over a region here where our variables are r and theta. Right? We're going to distinguish between the little r here and our vector r, and recall that what we want here to compute the surface area is we want to integrate over the region. If it's b here, we want to integrate over the region r, partial of r with respect to u crossed with partial of r with respect to v, where these are the vector value functions r, du dv. That cross product, we take the magnitude of the cross product here, right? Now, here what we have is the following. Our r, you can think of this as going from a theta little r plane here. Well, these are various values of theta and r. Right? Our vector r is going to be give us x, y, z, where x is equals to r cosine theta, y is equal to r sine theta, and z is equals to z of r and theta. So z is our function function here, z of r and theta. All right? The partial of r with respect to theta is equals to, with respect to theta here now, so that this is minus r sine theta, r cosine theta, and partial of z with respect to theta. That's the partial of r with respect to r, this is the vector value function r with respect to r here, is going to be equals to cosine theta, sine theta, and partial of z with respect to r. We wish to take the cross product of these two here then, and for that purpose, what? We're going to get an I component. It's going to be r cosine theta times zr jk minus z theta sine theta. This is the I component. We're going to get, for the cross product here, for the j component, we're going to get z theta cosine theta ki minus ik, so plus r sine theta zr, that's the j component. And for the k component of the cross product, we're going to get ij, that's minus r sine squared theta, minus ji, that's minus r cosine squared theta. That's the k component. All right? Well, here we've got sine squared plus cosine squared, so that this is essentially minus r. What we now wish to do is we wish to take the magnitude of this vector here. So that means we take the k component squared. This is essentially r squared. The j component squared, what do we get? We get plus z theta squared cosine squared theta plus r squared sine squared theta zr squared plus 2 times the cross product here. So this is 2 times z theta cosine theta sine theta zr. Right? That takes care of the j. Then we need to square the I component. We get r squared cosine squared theta zr squared, and we get z theta squared sine squared theta. Right? And now we've got minus 2 times this product squared, but that's exactly going to cancel with this here, so that we're going to not have this term appear here. It's minus 2, it's the middle term here in squaring this. So now what have we got? Well, we've got r squared, right? Here we've got z theta squared cosine theta, here we've got z theta squared sine theta squared, and so the sum of these two is going to be z theta squared. And then here what have we got? We've got r zr squared sine squared, and here we've got r zr squared cosine squared. So we're going to get plus r zr quantity squared. We integrate this over our region B with respect to r and with respect to theta. This then will give us the surface area. Right? I want the magnitude of this, so it's going to be the square root of this. Right? The magnitude of r theta cross r over the region B. So square root r squared plus z theta squared plus r zr squared dr d theta. There's no multiplier in here. This is the actual integral. And so this is an example of how to get a formula for surface area when you're dealing with a math